Welcome to this new class. So, what we will do first is to review the last lecture, which is 13th lecture. So, in this lecture we discussed about the polar ionic transport, which is nothing but related to mechanism of conduction in ionic solids. So, unlike metals and semiconductors where transport happens in the bands, where electrons or holes move in the bands, here in ionic solids it is the polar ionic transport. Now, this polar ion is nothing but it is a charge carrier which is in the proximity of the lattice, and this proximity of the lattice leads to polarization of the lattice, and this leads to a combined entity sort of lattice and the lattice ions and the carrier, and this is called as polar ion. And this proximity also changes the effective mass of the electron, and it usually it is heavier than the mass of free electron. So, and also since it is associated with the lattice, it moves from one side to another. So, it happens by hopping of carrier from one side to another. As a result, it is temperature dependent. So, mobility in this case becomes temperature dependent in the form of exponential minus q by kT, unlike in the case in metals and semiconductor where it is dependent T to the power minus 3 by 2 form, which is due to scattering. So, the dependence of temperature in some metals and semiconductor, dependence on temperature of mobility in metals and semiconductor and in ionic solids is due to different reasons. As a result, you have different dependence. And then we looked at the case for example, how does the resistivity changes in ionic solid, for example, in a doped oxide. Then we looked at what is ionic conductivity in these materials. Ionic conductivity is nothing but Ci, Zi, E, mu I, and you know what mu I is. Mu I is nothing but the ionic mobility, and so you can see that resistivity or conductivity has a similar relation to temperature as diffusivity has, simply because it is proportional to, and again proportional to diffusivity. And similarly, just like diffusivity, it also has extrinsic intrinsic regions. In case of impure solids, there will be extrinsic region where conductivity will be governed by the concentration of impurities, and there will be intrinsic region where conductivity is going to be governed by intrinsic defects. And then we have this ionic conduction. We looked at a transference number, and this transference number is nothing but ratio of ionic or electronic conductivity to the total conductivity. So, any type of conductivity divided by total conductivity, because total conductivity is sum of all sorts of conductivities. So, for a perfect ionic conductor, T will be equal to 1, T ionic will be equal to 1, and for perfect electronic conduction, T electronic will be close to 1. And then we had to look at the certain material systems, and then we chose an example of magnesium oxide. So, what we found in this example was that in the pure form at 1500 degree centigrade, sigma electronic is much larger than sigma ionic. So, what we will do in this class is we will look at what is the effect of doping on conductivity. So, and effect of now, this is because magnesium oxide is prone to having impurities. So, it contains about 400 ppm of roughly aluminum ions in the form of Al2O3. Okay. So, now you can write the defect reaction as you can. So, Al2O3 going to Mg, sorry, so Al going to Mg site, and it is going to give rise to one positive charge. So, since both the aluminums go to magnesium sites, you have you can have various scenarios. One scenario could be all the 3 oxygens going to oxygen sites, creating one vacancy of magnesium, or giving rise to all the excess oxygen goes out and giving rise to electrons. So what happens in this case is vacancy concentration is dependent upon the concentration of aluminum oxide. So you can see Vmg from this relation is equal to half of AlMg. So if you know the concentration of Al2O3, you can work out concentration of aluminum ions. From that you can work out what is the concentration of vacancies. So using simple principles, you can convert mole percent into per centimeter cube. So this 400 ppm works out to about 2 into 10 to the power 19 per centimeter cube. And since you know that, so this is your aluminum concentration. So your V mg is about half into 2 into 10 to the power 19. So this will be 1 into 10 to the power 19 per centimeter cube. So this will be your concentration of excuse me. So here we have got, I am just trying to work out what is, so Vmg AlMg is equal to twice of Vmg. So Vmg is half of AlMg. Okay. So we are right there. So 1 into 10 to the power 19. So now from this you can work out what is sigma ionic. Sigma ionic is nothing but your basically sigma Vmg, which is nothing but ZVmg multiplied by E multiplied by CVmg multiplied by mu Vmg. Okay. Now mu Vmg we have already calculated, CVmg we know what it is, electron charge we know, and ZVmg is 2. Okay. So that this would be 2 into 1.6 into 10 to the power minus 19 coulomb multiplied by 2 1 in, sorry, not 2 but 1 into 10 to the power 19 per centimeter cube multiplied by mu, which is nothing but 7.6 into 10 to the power minus 6. If you go to previous slides, one of those, we worked out mu as mu to be 3.3 into 10 to the power minus 6. centimeter square per volt second. Now, so this will be your approximately 3.2 multiplied by 3.3, approximately 10 multiplied by 10 to the power minus 19, minus 19 plus 19 will cancel each other, 10 to the power minus 6. So this will be in ohm centimeter inverse, and this will be 10 to the power minus 5, approximately, I am saying approximately equal to 10 to the power minus 5 ohm centimeter inverse. Okay. So now if you go to next slide, now electronic conductivity has to be either due to electrons or holes. Now we have calculated what the intrinsic electron concentration is. We know that intrinsic electron concentration was 3.6 into 10 to the power 9. Now let us see what is the electron concentration due to defect creation. Okay. So under in the normal atmosphere, so let us say normal atmosphere case, now this means PO2 will be equal to 0.21 of atmosphere. Okay. So this we treat as a oxidizing condition. Under these conditions, your half O2 goes in, gives rise to Vmg plus OOX plus H dot, 2H dot. Okay. So so your NH is equal to 2 Vmg. Okay. So, from this you can calculate what NH is. Now, you know that oxidation constant you can calculate as Vmg into NH square divided by Pu to the power half from this reaction, and this is given as 10 to the power 64 multiplied by exponential minus of 6.24 EV by kT. Okay. So, from this at 1600 degree centigrade in air, there is a correction to be made in the previous slides, and that is here it should be 1600 degree centigrade, not 1500. That is the only change. So, at 1600 degree centigrade in air, I can calculate using this expression. From this I can calculate what NH would be, and this NH works out to be 5 into 10 to the power 13 per centimeter cube, and this whole concentration works out to be much larger than the electron or hole concentration which are thermally generated, which are of the order of 10 to the power 9. So, we will ignore those, and now if you calculate the electronic conductivity, sigma electronic, this will, because the electron concentration is very small as compared, because thermally created electron or hole concentration is very small. So, we can approximate this to NH E into mu H. Okay. So, this NH we can take as 7 centimeter square per volt second mu H, and NH we know from that. So, sigma electronic is NH is 5 into 10 to the power 13 per centimeter cube multiplied by 1.6 into 10 to the power minus 19 coulomb multiplied by 7 centimeter square per volt second, and this will come out to be 7 to 535 . So, this will work out to be 5.6 into 10 to the power minus 5 ohm centimeter inverse. So, if you compare the two values now, so sigma ionic was 10 to the power minus 5 ohm centimeter inverse. So, now if you compare these two values, they are not vastly different. I mean, they of course, the electronic conductivity is still higher, but if you calculate the T ionic is merely 1 by 5.6. Now, this works out to roughly approximately. So, this is basically 10 by 56 or 100 by 56 into 0.1, approximately 0.1 and 44, and then approximately 0.18, which means T ionic is, T electronic is approximately 0.82. So, what it means is that this is a mixed conduction, because here 20% approximately 20% of the conductivity is carried by ionic conductivity, and remaining about 80% is carried by electronic conductivity. So, this is a good case of mixed conduction. Now, if the ionic conductivity becomes much higher than electronic conductivity, then you of course call it a ionic conduction. So, this is one of the example where we saw that magnesium oxide in the pure form at 1600 centigrade is a perfect electronic conductor, because electronic conductivity is much higher than the ionic conductivity, and when it is in the impure form, the ionic conductivity increases as a result of presence of impurities, which give rise to presence of extrinsic vacancies, and this leads to significant increase in the ionic conductivity, and it becomes a mixed conductor. So, you will have some more exercises of the same kind in the exercises, same problems. So, you can solve them and get a feel of what it is basically about the ionic defects, effect of ionic and electronic defect concentration on the conductivities, and of course, the effect of diffusivity and mobility. So, this is sort of this, I hope makes it clear the distinction between ionic and electronic conductivity. Now, so far we have discussed ionic conduction in a very qualitative manner. We have derived an expression from the Nernst-Einstein relation which relates ionic conductivity to the diffusivity. Now what we will do is that we will go back to fundamentals and derive the equation for ionic conductivity right from the basics, which means starting from the hopping model, and we will see whether what we get here is same as what we have derived from Nernst-Einstein equation or not. So, so basically the picture is something like this. So, we will develop a quantitative model for ionic conduction. So, now as you know that as we have discussed that ionic conductivity is a hopping kind of model, where the carrier moves from one side to another, and this could be movement of carrier from one site of different charge to another site of another charge, or it could be counter migration of defect and the occupied site. Now usually it is defect, you can consider it has a counter movement of defect and the filled site. So basically the conduction will depend upon if an atom wants to move, it has to have a vacancy near it, otherwise it can't move. So it depends upon the presence of vacant sites in the vicinity of the mobile ions, let us say. So what happens? So if you want to draw now a picture, a potential energy picture for example. So let us say in a lattice you have various ions sitting, okay. So I will just make a one dimensional picture. All these are spherical, they are not elliptical, supposed to be spherical, okay. And let us say one of these site is empty, okay. So I will make this site as empty site, all right. Now what will be the potential energy diagram for this? So if I draw the potential energy diagram looks something like, oops, okay. So this is a sort of potential energy diagram, and this is the potential energy barrier delta EA, you can call it. So this is also like activation energy. So now you have this various sites. So this site can move to this side, so basically this vacant site can move to right side, but it can also move to left side, because in the absence of electric field, now this is the condition when E is equal to 0, okay. So in the absence of electric field, this vacant site has equal probability of moving whether to right or to left. Now what happens when you apply electric field? When you apply electric field, then the same picture changes a little bit. So what happens is, depending upon the direction of electric field, let us say the direction is this. So here now what happens is, the okay. So now these are of course not up to the scale. So let us say this distance is delta, all of them are delta, okay. So delta is basically the spacing between two lattice sites. So here again this is delta, this is also delta. So let us say this was your vacant site, these were your filled site. Now what has happened is, now if you look at the energy barrier, the energy barrier on this side has decreased by this much amount, because now the energy barrier is only this much, and on this side, other side, the energy barrier has increased by certain amount. And what is this amount? This amount is nothing but, so let us say this amount is delta EA, this would be minus delta EA or let us say delta EA, let us not add confusion here. So, and this would be again EA, delta EA. So, because the potential energy well is symmetric, so there is a symmetric displacement on both the sides, either on top or bottom. So, here, so if this vacancy, which is, let us say I make it red here. So, if this vacancy has to move to right, the energy barrier which was delta, which was EA earlier, sorry, I should make it EA, which was EA earlier, becomes EA minus delta EA, okay. And here on the left hand side it increases by the factor delta EA. So, there is definitely the probability of moving to either side also changes. So, we will treat it mathematically a little later. So, this happens when E is finite, okay, and we will see what delta EA is. So, basically the presence of electric field provides reduced barrier or higher driving force to one particular side than to other side, and this of course this ionic conductivity, as we will see, is also influenced by other factors, but this is the basic model that we are looking at. So, first the thing is, in the absence of field, so in the absence of external field, what is the probability that the side can move to either side? According to Boltzmann statistics, the probability is equal because the barrier is equal. So, let us say the probability is F. So, F can be given as half is the factor because it can move to either side, alpha is, let us say, some coefficient called accommodation coefficient, multiplied by nu is the natural frequency of vibration or vibrational frequency, multiplied by exponential minus of EA by KT. So, this is your typical Boltzmann equation. So, this alpha is nothing but accommodation coefficient, and this nu will be frequency of vibration, not vibrational, vibration, okay, and this would of course be in per second, and this is unitless. So, this is the probability of moving to either side. So, what happens now when we apply the field? So, when you apply the new field, then upon application of field E, what happens? Now, upon application of field E, as you see that energy wells have tilted to one side, which means the barrier to one side has decreased, another side it has increased. So, so let us say the ionic charge was Z, then what would be the force experienced? Force, let us say force given by the field, force exerted would be ZEE, okay, and as a result of this force the wells tilt on other side. So, the total change which occurs on either side, so the picture would be like this. So, you apply the field, okay. So, this is your half delta. So, it would increase, it would change by half f into delta on one side, and it would change by half f delta on other side. So, change in energy barrier on each side would be f into half delta, which would be half Z E delta E, okay. So, this is nothing but your delta EA, Now, whether delta EA would be positive or negative, it depends upon which side you are looking at. So, of course, on the right side it would be now, so barrier on right side, so barrier on right hand side would be EA minus half of ZE delta E, and on left hand side it would be EA plus half of ZE delta E. Okay. So, now we will look at what is the probability of movement on each side. So, probability of moving to the right will now be, so let us say I determine it as, I denote it as F right, and this F right would be half of alpha nu exponential minus of, now that this energy would be EA minus half Z E delta E divided by KT. That makes sense. Okay. So, what it basically means is that the probability also increase on the right, probability will also increase for movement towards the right. Similarly, to the LHS left hand side, this would be F again half alpha nu exponential minus of, it would be EA plus half Z E delta E divided by KT. So, you have a net movement on one side simply because the probability of moving to one side is higher. So, as a result, these ions which move, there is of course, the movement of vacancy is nothing but movement of ions. So, which means that these ions acquire a net velocity, and this net velocity is called as average drift velocity. So, I write it as average drift velocity of ions, simply because they drift on one side under the action of electric field, simply and that is because of higher probability of movement. So, this is given as V average is given as, so what would this be? F right minus F left, this is in per second, multiplied by the distance delta. Distance is the delta which they are covering, which is in meter or centimeter depending upon. So, this will be velocity unit meter per second, and this would be nothing but your half of, if you do the so this would be half alpha nu delta into exponential of minus of EA minus half Z E delta E by KT minus exponential of minus EA plus half Z E delta E by KT. It has become a little smaller on the, but so this would be basically EA plus delta EA, and this is EA minus delta EA. So, when you open this up, so now the net, so you can now write this as, so this would be V will be equal to, V average will be equal to, what we wrote was half of delta, you can write other expression as half of delta F into exponential of Z E delta E divided by 2 KT minus of exponential of minus Z E delta E divided by 2 KT. So, this is what it has reduced to the previous expression. So, now we know that exponential of x minus exponential of minus x divided by 2, what it is called as? This is called as sine of hyperbolic x. Okay. So, based on this principle, we can reduce this V average to delta f into sine of hyperbolic z e delta e divided by kt. Okay. So, this is what this drift velocity expression is reduced to. Now, under the normal circumstances, when ceramics operate, this field is not too large, it is very small. So, this field is typically, let us say, few volt per centimeter, or it is not very large field. So, what happens is that when this field is not very large, then this induced energy change is also very small as it is in comparison to thermal energy. So, this so basically what I am trying to say is, if this numerator is smaller than denominator, which means the field has to be smaller. So, basically this change in energy which is induced by application of field is smaller than thermal energy, then I can write. So, what I am saying is that half of Z E delta E is much smaller than KT, all right. So, what it basically means is that we can modify this equation and we can write V average is equal to delta F multiplied by Z E delta E divided by I have missed out 2 here. So, this would be 2 kt. So, this would be Z E delta E divided by 2 kt, and this so you can what basically I mean is that if so sine hyperbolic is x is equal to e to power x minus e to power minus x divided by 2, you can open up e to power x and e to power minus x. So, what basically it would mean is, if x is very small, so you can open this 1 plus x square by factorial 2 and dot 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 minus of 1 minus x plus x square by factorial 2 dot 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 divided by 2. If you ignore the higher powers, what it would mean is basically x. So, sine hyperbolic would be equal to x for small x. Okay. So, V average has become delta F multiplied by Z E delta E divided by 2 kt, and this would this is nothing but your Z E delta square F E divided by 2 kt. Now, we are very close to the expression of conductivity. So, what is the what is the expression for conductivity? Now, at low field strengths, we can assume that Ohm's law is perfectly valid, and as a result we can write this current density. So, at low field strengths, we can write current density as J is equal to N into Z E into V average, which is nothing but drift velocity. Okay. So, now this would be N Z E multiplied by delta square. What we wrote in the previous slide was Z E delta square F E divided by KT, right. So, this becomes equal to your N E square Z square delta square F E divided by KT. Okay. So, now we know what is F. Now, we know F is equal to half of alpha nu exponential minus of E A divided by KT, correct. So, if you know F, you just insert in there. So, that means J is equal to half of alpha nu multiplied by N E square Z square delta square divided by KT into exponential minus E A by KT into E, and from Ohm's law we know that J is equal to sigma E, where sigma is nothing but conductivity. So, now you get the expression for conductivity, and this expression for conductivity works out to be, so this particular part will be your sigma. So, your sigma is n alpha nu e square z square delta square e square z square delta square divided by 2 kt into exponential of minus E a by kt. So, now you can see the relation with the previous expression. In the previous expression we said that sigma was equal to ionic was equal to Ci Zi E into exponential of into mu I, okay, and this was made equal to Ci Zi square E square divided by kt. So, basically this was the expression, and this becomes your di. Now, di was d naught into exponential minus Ea by kt, because Ea is nothing but your activation energy needed for migration, right, which is nothing but your migration or diffusion energy. And this di term includes the same. Di is nothing but, if you remember what d was the term which included your nu, which is nothing but your vibrational frequency, and some other constants multiplied by exponential minus Ea by kt. So, now you see a correspondence between these two expressions. So, basically this expression is also nothing but sigma is equivalent to, sigma is proportional to exponential minus Ea by kt. So, basically this analysis has explained that no matter how you derive the ionic diffusivity, ionic conductivity, the conductivity is similar, the form is similar, it is always proportional to exponential minus Ea by kt or Qa by kt or Hm by kt, depending upon the convention, and this energy is the migration energy. Okay. So, I will give you some of the values now. So, for example, some of the glasses, and then activation energy, and show you how these values match with each other. So, for example, these glasses have composition of Na2O, CaO, Al2O, SiO2. So, this is let us say 33.3% and 66.67%, and this is an activation energy Ea, and one of these is from the conductivity data and another is from the diffusion data, and both of these you will see match. So, this conduction values work out to be 14 to 16, and these work out to be 13 to 14. So, this is in kilocalorie per mole, you can write the units. So, there is a fairly reasonable match between two values. For some other glasses, if you take 15.7, 12.1 and 72.2, again the values are 15.6 and 16.4, not too far, they are in reasonable agreement. And if you write one more, for example, 14.5, 12.3, 5.8 and 67.4, this gives you 19.5 and 20.2. So, you can see that the values of activation energies, whether you measure from diffusion data or conduction data, they are similar, which actually validates the model, that models are correct. If you want to look at the data of various materials, I would suggest you to go to Principles of Electronic Ceramics by Hench and west. Okay. So, this so now there are, so you got the basic idea about how to work out the ionic conductivity in ionic solids. So, I will now give you some more data about these materials. So, for instance, one of the very good conductors, ionic conductors are good ionic conductors are, let us say, your beta prime and beta double prime aluminas, and these have, for example, your conductivities are of the order of 10 to 10 to the power minus 1 ohm centimeter inverse. These are approximate values. So, of course, for each of these materials it will be a specific value, and so let us say between about 300 to 675 Kelvin. So, roughly in this range, and that activation energy or Q, sorry, let me not change the convention here, it would be EA. EA is about 3.5 to 4.5 kilocalorie per mole, which is a very low energy. You can also convert it to kilojoule per mole, and so this is so these come in the category of good ionic conductors. There are some other oxides such as Fe3O4 and spinels, which is nothing but Ab2O4 structured compounds. So, sigma for these is about 0.5 ohm centimeter inverse, and Q is very small, EA is very small. EA is of the order of 0.35 kilocalorie per mole, very, very small. What it basically means is that the temperature, if you plot log sigma versus 1 by T, the plot will be almost flat. So, almost temperature independent behavior, whereas in case of other oxides like insulating oxides, like yttrium oxide, hafnium oxide, silicon oxide or aluminum oxide, in all of these cases the conductivities are in the range of 10 to the power minus 5 to 10 to the power minus 14 ohm centimeter inverse, very, very low values, and this is over about 400 to 1000 K, and activation energies can be mixed. So, these are distinct materials which have distinct values of conductivities. Now, in the case of conducting ceramics, you have two categories. One is called as glasses, and second is called as in the category of glasses you have molten silicates as well, and then second you have fast ion conductors. So, first we will look at the glasses. Now, we have not discussed the structure of glasses in detail in the structures, but the only difference with respect to crystalline materials is that these are these materials do not have periodic arrangement of ions. As a result, they are amorphous. That is why they are called as glassy. They have a glassy behavior, which means when you melt them, they do not have a specific melting point, rather they have a softening point, and their viscosity tends to increase, and then they completely become fluid. So, this low viscosity at reasonably low temperatures makes the glasses very useful in terms of fabrication, because you can blow them and form them in different shapes. So, glasses basically have a random 3D network, and they typically contain the glass forming agents. If you put because if you put all the basically they are all silicates. So, there are various forms of silicates, many crystalline form of silicates as well. For example, quartz is a crystalline form of silicate. Now, in order to form the glasses, typically you use the agents. So, these agents are your impurities like boron oxide, you could have aluminum oxide, you could have many other impurities, which are called as glass forming agents. And basically what happens here is when you put these agents, so normally what you would have is a SiO4 tetrahedra. Now, within these SiO4 tetrahedra, so in between you have silicon ion, and this is O. So, what happens is that when you put these ions, notice that these ions do not have similar valence as of silicon. So, what happens is that they attach themselves to the ends of these tetrahedras, reducing their corner connectivity. So, a lot of these tetrahedras hang around in the 3D space just with the loose ends. So, as a result, they do not have an interconnected structure, and they tend to have lower melting point or softening point. So, these are so basically you have two types of ions. One is a modifier ion. Now, modifier ions are ions typically which basically increase the conductivity, and these are your smaller sized ions, sodium or potassium, okay, or lithium. And then you can have blockers or blocking ions, and these blocking ions tends to be bigger sized cations such as calcium or magnesium. The increase in the conductivity upon addition of these ions is much larger than upon the addition of these ions. Okay. So, that is why there is a relative effect. These are called as modifier, these are called as blocker. Now, of course, as you increase the temperature, the conductivity increases because the barrier for migration of these ions increases, and also as you can understand intuitively, the conductivity would depend upon ease of migration, which means smaller the ion is, smaller the mobile ion is, larger the conductivity would be. In these cases, now the important thing about glasses is that they are commercially important. Commercially important means they have to be made by furnaces. Now, they have to be melted by the furnaces, and typically they are melted in electrical furnaces. And now, when you melt them in electrical furnaces, then resistive heating of the glass is the mechanism which is used to melt them, which means the resistivity is an important factor. They cannot be too insulating. If they are too insulating, you cannot use them for heating purposes. You cannot melt them in a furnace using resistive heating. So, how do you tune this electrical resistivity? The electrical resistivity or electrical conductivity of these glasses is tuned by adding various impurities such as your alkali ions or alkali earth ions. So, for example, for alkali oxide addition, let us say it is R2O. So, R2O greater than 22%, the highest conductivity sigma Li2O. Now, sigma Li2O means conductivity of glass upon addition of Li2O is larger than Na2O, which is larger than K2O. But for R2O less than 22%, sigma of Na2O is the highest, followed by sigma of K2O, followed by sigma of Li2O. So, you can see that although here you have a clear cut relationship with the size, here you do not have really a clear cut relation with the size. So, intermediate ions such as sodium gives highest conductivity, and there is you can draw a plot as well. So, when you plot the resistivity of these glasses, there is a relation with ionic size. So, let us say log resistivity versus ionic radii, let us say in angstrom. So, let us say this is 0.5, this is 1, this is 1.5, and this let us say is about 7, 8, 9 and 10. Okay. So, the effect of beryllium would be somewhere, this dashed line is the resistivity of modified Na2O SiO2 glass. So this is so this Na2O is 20% in this. Okay. So when you put beryllium into this, the addition of beryllium increases the beryllium is somewhere here. This would be beryllium. Magnesium zinc would come somewhere here. So magnesium, your zinc. The increase of calcium goes somewhere, calcium is between here, and so the basically it goes something like this. And there are various ions which form at various places depending on the size. So you will have barium somewhere here, then somewhere here will have lead, then strontium, etc., etc. So the range of conductivity basically is from 10 to the power minus 6 to 10 to the power minus 10, or so resistivity 10 to the power minus 7, 10 to the power minus 6 to 10 to the power 11 ohm centimeter. So basically in glasses the conductivity, so sigma at room temperature varies from 10 to the power minus 6 to 10 to the power minus 8 ohm centimeter inverse. So this is the typical conductivity of the silicated glasses at room temperature, whereas for alkali earth elements, sigma CaO is larger than sigma MgO, which is larger than sigma SrO, which is larger than sigma BaO. This is a typical trend, but the differences in this case are smaller differences as compared to alkali ions. So the effect on the increase of conductivity of silicate glasses is very large in case of alkali ions than in case of alkali earth ions, because alkali ions are much more smaller and alkali earth ions are bigger, and once the ion becomes a bit too bigger, the effect on the conductivity is insignificant. Another category of conducting materials is conducting ionic solids is fast ion conductors. And these are also called as FICs. Now fast ion conductors are the materials which show very large ionic conductivity, much larger than a typical ionic solid, as we saw just a few slides ago in case of beta alumina. So these conductivities sigmas are typically greater than 10 to the power minus 2 ohm centimeter inverse. So these are typical values and at temperatures much lower than the melting point. Typically in a ceramic, what you would expect is, as the temperature increases very close, and when it reaches very close to melting point or at least half of melting point, then the conductivity starts increasing. Here the conductivities are much larger even at very low temperatures, and this is because of, first of all, the number of mobile charge carriers, which depends upon the number of mobile ions. So the fraction of ions which are present at mobile ions which can actually move is much larger, so than in a normal ionic compound. So what happens, let us say, is N naught is the number of potentially mobile ions, and let us say N prime is the number of actually mobile ions. So this ratio N prime by N naught in fast ion conductor is much larger than in a normal ionic solid. So that is why that is one reason. Second reason is that the diffusion energies are very small, and in many of these compounds the structure tends to be very open. So, the migration energy requirement in order for these ions to move is also very small. So, what we will now do is we will categorize them into two categories. So, one is intrinsic FICs. So, in the intrinsic FICs we have materials like halides and chalcogenides. So, halides and chalcogenides of typically silver and copper, such as AgI. So, here mobile ion is Ag plus, okay, and many of these Ag ions are mobile. And you can have alkali metal conductors such as beta alumina structured sodium aluminates. So, these are for example beta Al2O3, this is nothing but your Na2O dot 11 Al2O3. So, here the mobile ion is Na plus ion, and many of these sodium ions can move. So, monovalent sodium ions are highly mobile ions because of their smaller size and also the open structure. And then you have extrinsic. So, the previous compounds are intrinsically mobile. So, you are not doping them with anything. So the structure is based on parent ions, and these parent ions in the lattice are the mobile ions. In the extrinsic FICs, you have to intentionally dope them. So, for example, zirconium oxide doped with aliovalent. Aliovalent means ions having different valence impurities, such as yttrium oxide or calcium oxide. And here the delta here, this basically what it does is it creates defects which could be in the form of oxygen vacancies, okay. And moreover, these zirconium oxide structure is based on fluoride structure, which is an open structure. If you recall the structures, go back to structure module and you will recall that the structure of zirconium oxide is an open structure. So, when you create oxygen vacancies by these means, these oxygen vacancies tends to be very mobile, and the enthalpy of migration in these materials can be extremely low, which gives rise to large conductivity in these materials. So, these are extrinsic fast ion conductors are those which are intentionally doped with some impurity in order to increase the defect concentration, and they have open structure which gives rise to larger conductivity. So, I'll basically give you some examples of these materials, and then I'll finish off this lecture. So, FICs and conducting ions. So, if you take cubic zirconia, oxygen ion is the conducting ion. Naturally, if you create oxygen vacancies, which means oxygen ion would be the conducting ion. And similarly, if you have boresite, for example, Li4B7O12Cl, this has lithium ion as mobile ion. If you take Ag2O, Agi, B2O3, so you can say FIC slash glass, okay. Here your Ag plus is the mobile ion. In silver iodide, Ag plus is the mobile ion. In beta Na-Al11O17, your sodium plus. So, these are some of the examples. So, basically what we have done in this lecture is we have developed a quantitative model for conductivity in ionic solid using Maxwell-Boltzmann statistics upon the under the application of electric field, and we found that the expression which we get from here is similar to what we got from Nernst-Einstein relation, and basically this conductivity is related to exponential of minus of migration energy divided by kT. So, these two expressions are similar, which validates that what we have done is right, and then we compared the experimental and theoretical values, and the values obtained from diffusivity data, values obtained from conductivity data, and both of them match reasonably well. So, that gives us confidence that our model was right. And then we looked at some of the examples of conduction in various glasses and fast ion conductors, and found that these glasses and fast ion conductors can be significantly conducting as compared to normal ionic solid, which are typically insulators. So, what we will do here is we will finish this lecture here. In the next lecture, we will take up the topic of electrochemical potential, and we will look at certain examples of these ionic solids, conducting ionic solids in practical applications. Thank you.